previous section, we learned that some acids are strong. On the other hand, some acids are weak. Similarly, some of the bases are strong while others are weak. The strength of any acid or a base is a relative term. So the property by which we can measure a strength of any acid and base is called pH. pH measures the concentration of hydronium ions in aqueous solution, and because acids produce hydronium ion in aqueous solution, so in turn it can also be used to measure the strength of acid. The concentration of both hydronium ion and OH negative ion is expressed in molar concentrations, which has the units of moles per liter. It's also known as molarity. Depending on the concentration of hydronium ion, the pH value can be anywhere from 0 to 14. pH value of 7 or below means that our solution is acidic. So any value of 7 or below means that the solution is acidic. If our solution has a pH value anywhere between 7 to 14, then our solution is a basic. Basic solutions are also known as alkaline solutions. At 7, if the pH is exactly 7, then our solution is neutral. In acidic solutions, the concentration of hydronium ions is more than OH negative. So in other words, there are more hydronium than the OH. In basic solutions, the concentration of hydroxide is more than the hydronium ion concentration. At neutral point or at pH 7, the concentration of hydronium and OH negative becomes equal. Understanding of pH is extremely important in medicine and physiology. It has been found that blood plasma pH is an important indicator of health. Blood plasma normally has a pH value of 7.35 to 7.45. This is known as physiological pH. When blood plasma pH falls below 7.35, it causes a medical condition called acidosis. If the blood plasma pH rises above 7.45, then it causes a medical condition called alkalosis. Both acidosis and alkalosis are life-threatening conditions. Other body fluids also have specific normal pH values, and these values are shown in this table. In human body, a proper organ function requires a blood pH value to be between 7.35 and 7.45. pH is maintained in human bodies by a process called acid-base homeostasis. Many medical conditions, including kidney disease, stroke, depression of respiratory center by drugs and poisons, can cause acidosis or alkalosis. Acidosis is a condition in which the pH value falls below 7.35. Alkalosis is a condition in which the blood pH value rises above 7.45. From this chart, it is clear that both of these conditions are potentially life-threatening, and a pH value of above 7.8 or pH value of below 6.8 may result in death. Fortunately, in healthy human body, pH is maintained within this range by this process of homeostasis. As part of normal cellular metabolism, substances that affect blood pH are produced and released into the blood, as shown in this picture. This section represents the muscle tissue, and the top layer represents the blood flowing in capillaries. The key molecules or ions which affect the blood pH are dissolved carbon dioxide and the hydrogen ions. These two molecules or ions will dissolve in blood, and they will change the pH, as we know that H positive ion causes the pH to drop. So releasing of these two species into the blood will result in change in pH. The pH of blood is maintained by a uh, property called buffer action. We will learn more about buffers in later in this chapter. So buffer action is a technique or is a method by which the pH of any solution is kept constant. The main substance which is responsible to maintain the pH of blood is carbonic acid, which is shown here. Now, carbonic acid can dissociate into water and carbon dioxide, and carbonic acid is produced when H positive ion combines with the bicarbonate ion. So if the pH of blood drops below a certain value, which is 7.35 as we know it, our body responds by increased uh, respiration. So increased respiration means that majority or more carbon dioxide will be expelled out. So that will create a negative depression on this side of the reversible reaction. It means that equilibrium will shift to the right. If the equilibrium shift to the right, we will have lesser amount of carbonic acid. That would mean that this equilibrium will also shift to the right. Shifting to the right means now we have less uh, hydrogen ion, which means that pH will go up. So this is the response of our body when there is more hydrogen ion in blood, which are causing the pH to drop. If the pH of our body increases above, then the opposite will take place. In that case, the equilibrium will be shifted to the left hand side, resulting in high concentration of carbonic acid, which would increase the production of hydrogen ion, and hence the pH will go up. With this action, the pH of blood is maintained within the values of 7.35 to 7.45. Earlier in this chapter, we learned that water is an amphoteric substance, which means that it can act as both acid as well as a base depending on the condition. Even in pure water, small concentration of water molecules react with other water molecules to produce hydroxide ion and hydronium ion. This is known as autoionization of water. Autoionization of water occurs when very few water molecules react with other water molecules to produce hydronium ion and hydroxide ion. So essentially, in this reaction, water itself is acting as an acid as well as a base. In pure water at 25 degrees Celsius, the concentration of hydronium ion is measured to be 1.0 times 10 to the negative 7 moles per liter. And the concentration of hydroxide ion is also measured to be 1.0 times 10 to the negative 7. Because the concentration of both hydroxide and the hydronium ion are equal, so technically it is a neutral solution. The equilibrium constant of this reaction is abbreviated by Kw, and it is known as ion product constant for water. Ion product constant for water can be found by multiplying the concentration of hydronium ions and the concentration of hydroxide ions. As we learned earlier that both hydronium ion and hydroxide ion concentration is 1.0 times 10 to the negative 7. So the product of both hydroxide and hydronium ions is equals to 1 times 10 to the negative 14. This is known as the value of ion product constant of water, and this value is always uh, equals to 1 times 10 to the negative 14. So the value of Kw is always constant, and it is equals to 1 times 10 to the negative 14. So it means that we always know the value of Kw. So in case we know the value of H3O positive, it is possible to calculate the unknown value of hydroxide. So in other words, if one of the parameters, either the hydronium ion or the hydroxide ion, is given, it is possible to calculate the other value by applying this equation. So in pure water, the value of Kw is equals to 1 times 10 to the negative 14, and Kw is given by the product of H positive ion concentration and OH negative ion concentration. If we add acid to the water, that would mean that the H positive ion concentration will go up. But interestingly, the Kw value never changes. So it means if the H positive value goes up, because Kw is constant, the OH negative value will go down. Similarly, if we add base into our solution, addition of base means the value of OH negative will go up, and because Kw value never changes, so that means that in order to maintain a constant Kw value, the value of hydronium ion will go down. So in other words, if one of the parameter, either hydronium ion or hydroxide ion, goes up, the other one will go down. So let's use the concept of ion product of water to solve this problem. In this problem, we have an aqueous solution with hydronium ion concentration of 1 times 10 to the negative 3. So in other words, we know the concentration of hydronium ions, and it is equals to 1 times 10 to the negative 3. And we want to find the concentration of hydroxide ion. So this is unknown, and we would like to find it. From the autoionization of water, we know that Kw is equals to hydronium ion concentration multiplied by hydroxide ion concentration. And we also know that Kw is equals to 1 times 10 to the negative 14. So therefore, from these two, we can say that H3O positive multiplied by hydroxide ion concentration is equals to 1 times 10 to the negative 14. So now we know the value of H3O positive. This is a constant value. So if we plug in the value of H3O positive, it is possible to calculate the hydroxide concentration. So let's plug in the value. So we will get 1 times 10 to the negative 3 multiplied by the hydroxide ion concentration equals 1 times 10 to the negative 14. So therefore hydroxide ion concentration will be equals to 1 times 10 to the negative 14 divided by -3, and if we use our calculator we will find that the hydroxide concentration uh, is equals to 1 times 10 to the negative 11. pH values can be calculated from the hydronium ion concentration using this equation. Let's take a look at one problem. A sample of blood has hydronium ion concentration of 4.0 times 10 to the 8 molar. What is the pH? In this case, the concentration of H3O positive ions is given, which is equals to 4.0 times 10 to the negative 8 m. So what is the pH? So pH is equals to, according to the formula, it's negative log of 4.0 times 10 to the negative 8. And this value, log of 4.0 times 10 to the negative 8 is negative 7.398, and that comes out to be, so this negative times negative will be positive, so that's 7.398. so pH value is 7.398 and it is within the normal value, so this blood sample is okay, it's normal. In many cases, the pH value will be given to us and we would like to calculate the concentration of hydronium ion. In that case, we can apply this equation to calculate the concentration of hydronium ion if the pH value is given. Let's take a look at this problem. In this case, a sample of stomach acid is given and its pH value is 2, and we would like to find how much hydronium ion concentration is there. So pH is given, so pH is equals to 2. So hydronium ion concentration according to this formula is equals to 10 to the negative pH, and that's equals to 10 to the negative 2. And if we solve this one, this value comes out to be 0.01.